Alright, so today we're going to look at section 1.5, which is on transformations. We're going to focus on looking at transformations of quadratic functions. Now, if you graph a quadratic, what's the shape of it? Parabola. Okay, so we're just looking at parabolas, and we're going to transform them. Now, once you know the transformations for a parabola, if you can tell me what that would do, adding a +3 on the end of a squared function, then you should be able to tell me what adding a +3 on the end of a square root function would do. It's going to do the same thing. That's a shift up 3 in both cases. So once we know the transformations, you know them for every function, okay? Whether it's squares, square roots, anything, any function we study all year. So a quadratic function is written in the form ax squared plus bx plus c, where a, b, and c can be any real number you want, except a can't be 0. How come? Bless you. What would happen if you made a 0? What would that do to your function if you made a 0? Oh, Chris?
No, it won't work.
What would happen? Yeah, so fill in 0 for a, and now what happens there?
X becomes 0 as well?
No, x can still be anything you want. Not sure. Nikira, can you help him out? What would happen if a was 0?
Part would be 0.
What part would be 0?
The x squared.
The x squared part, right? This whole part would disappear, because 0 times anything would be 0. And what would you be left with now? And what's that? Yeah.
Slope intercept form?
Yeah, that's a line. So if you made a 0, you just wiped out your quadratic term. You don't have a parabola anymore. Now you have something in slope-intercept, right? So a, b, and c can be any number you want, except a cannot be 0. So let's graph y equals x squared. Okay, just to look at a picture of it. Okay, I'm going to do zoom 6. I'm also going to turn off the shading that we had turned on in the homework. To turn it off, if you just clear everything out, it should go back to normal. So x squared, zoom 6. Okay, so there's a parabola. Now, let's see what happens if we plug in a negative x. Okay, let's try it. So I'm going to replace x with negative x. All right, so I'll go back to y equals. I'm going to leave, but I'll leave the original there so you can compare it. And I just changed x to negative x. What happened? Alex?
It's the same slope.
It's the same.
Parabola.
Yeah, it's the same parabola. So putting a negative in didn't make a difference. And that's kind of like if I said to you, square the number 2, square the number negative 2. Doesn't make a difference. It's the same answer. So when we put a negative inside, you can't really tell what happened. But how about if I did this? Let's go negative x squared. So now the negative is on the outside in parentheses. And see if you can tell me what happened this time.
Reverse the parabola.
Yeah, what did it do to it?
It reflected it across the x-axis.
Exactly. It reflected it, it flipped it, made a mirror image. So when we see negatives, right, it's going to create a mirror image. So technically, y1 and y2, those are mirror images of each other. But you can't tell because a parabola is symmetrical right down the y-axis. If you have something that's symmetrical, like a circle, and you do a mirror image of it, it looks the same. You can't tell that you did anything. So a parabola is not a good one to do a mirror image, flipping it left to right. But flipping it up to down, you can definitely tell that we flipped it. All right? So again, the reason you couldn't tell with the first one I did is because the y-axis is in line of symmetry. Now parabolas, this particular parabola, the one that I have in red, contains a low point that's called a vertex. Now the one in black also contains a vertex, but it's the high point. Okay, so a vertex can be a low point, or it can be a high point if you flip the parabola over. Any questions on that? All right, so that's just a little background on parabolas. Now we're going to start getting into transformations. How can we shift them vertically and horizontally? And how can we stretch them vertically? We're not really going to look at horizontally today. We will eventually with other functions, but not so much with parabolas. All right, so first thing we're going to look at is what happens if you change the number in front of x squared. Let's see what it does. So I'm going to keep the original, but I'm going to get rid of these other ones. And we're going to put in 1/3 x squared, and we're going to put in 2x squared. Right, so let's graph it and see. So the blue is the original. That's the 1/3 x squared. And the one in black is the 2x squared. So what did changing that number do? Yeah, Jared.
It widened it or made it more narrow.
Yeah, so what we're going to talk about for this transformation is what happened to it vertically. The options are either going to be like a vertical stretch or a vertical shrink or compression. So imagine that all these parabolas are glued right at the origin, okay, right there. Well, if they're all glued right there, and you took the ends of the parabola in blue and pulled it up, okay, it would stretch it out. It would make it taller and thinner. Like if somebody took you and like stretched you out, pulling you up, right, you'd get taller and skinnier. That's what happened to the one in black. It was stretched vertically. The one in red was compressed. Okay, so imagine, again, that one in blue is glued down right at the origin, and you took the sides of the one in blue and you pushed down on it. Well, just like if somebody pushed down on you, you would get shorter and kind of spread out, okay? Like Play-Doh, if you squish it down flat, it spreads out. All right? So that's basically what the number in front does. Either stretches or compresses. How do you think you can tell just by looking at the number whether it's going to stretch or compress? I gave you an example of each here. Yeah.
If it's a fraction, it's going to stretch.
So the one in red is the 1/3.
Or not stretch, shrink.
Yeah, so the 1/3 caused the graph to compress. And if I put in something like let's say I did 1/6, it would compress even more, right? If I put in a number like, let's change the 2x squared to 6x squared. Okay. What's going to happen now is it's going to stretch and be even skinnier. Yeah.
So any number less than 1 but more than 0 will compress it.
Any number that is less between 0 and 1 will compress it. Yep. We'll talk about what happens if it's a negative, but we kind of already saw what happened. It causes a flip. So, what's the effect of changing A? Well, if you make A bigger than 1, it's going to stretch your graph out vertically. And like Elias just said, if you make A between 0 and 1, it's going to shrink your graph. Well, the graph is compressed vertically, or shrinks down. I like the word compressed better. Any questions on that? So in the homework, they're going to ask you a question and say something like, which graph is above the other? Okay. If I was answering that question here, I would say the red graph is below everything. It's underneath all of them. The black graph is above everything. Okay. And the blue graph is in the middle. Okay. The only places where the graphs are not above or below each other is at the origin. They are all at the same point. But other than the origin, the red graph is underneath everything. Okay. All right, so we don't have to graph these. They're the same problems, just throwing a negative in front. Can someone remind me again, what happens when you put in a negative? Yep, over which axis? The x. Yep. When you put the negative outside parentheses, okay, kind of think of it like that. It causes your graph to flip. All right? You can try it on a couple. We already did one together. But the negative causes the graph to open downward. So if you were looking at a problem like this, there's actually two things happening. The 2 is doing something, and the negative is doing something else. Let's look at an example. So these kind of problems, I'm going to ask you, how would you change this into that? Okay? And there's two things that are happening. You do have to list them in a certain order, but later on I'm going to give you the order. Okay? So for now, I'm just going to kind of help you with it. So start with the 5. What does the 5 cause the graph to do? Yeah, Chris?
To stretch.
Yep, in which direction?
Down. Negative x. The opposite.
So think back to how I wrote it in the notes on the other page. I said if A is greater than 1, it causes the graph to what I wrote. Yep.
Stretches it vertically.
Yes. So the way you write this is you say vertical stretch. And then you have to say how much. This is a vertical stretch by a factor of 5. Not negative 5. Okay, vertical stretch by a factor of 5. Okay, so vertical stretch by a factor of 5, that's the first one. And now, the negative. What does the negative also cause to happen? Yep.
Vertical reflection across the x-axis.
Yeah, it's a vertical reflection, or you can just say reflect. Some people say flip, that's fine too. Reflect over x-axis. Okay, when you describe a transformation, you usually have two things you have to describe. Like if you just say vertical stretch, you're not going to get points for that. Vertical stretch by how much? Okay? If you just say reflect, you weren't specific enough. Reflect over what? The x-axis or the y-axis. So just make sure you say it like that. Okay. Now, there is a certain order that is important. And the order starts to get important when you have tons of transformations in the same problem. Like you shift it left, you stretch it, then you shift it up, then you flip it. Well, those things I just said, you've got to do them in a certain order. And I'll talk about that order later on. But it's kind of like PEMDAS. If you do it in a different order, you're going to get a different answer. Okay? So we stick with a certain order. All right, let's try this one. So I'm going to graph x squared plus, well actually you know what, I'll graph just x squared. And then in the next one, I'll do x squared plus 2. Does anyone have a guess what is going to happen here?
It's gonna move up to.
Right, let's try it and see. So there's your original. And there's your graph been shifted up 2 units. There's no stretch that happened there. It literally just took the parabola you had and moved it. That's all it did. Just moved it up. So what do you think minus 3 would do?
Move it down, right?
Yep. So we'll write these out. So to get y equals x squared plus 2, you would shift y equals x squared up 2 units. That's how you do it. If you were actually going to draw a picture. Take y equals x squared, shift it up 2 units. And then to get y equals x squared minus 3, you want to shift the original. Okay? The original is a lot of times called the parent function. The parent function is just the simplest version of what you're doing. Okay? The simplest version of what we're doing today, which is graphing parabolas, is y equals x squared. It's the most basic one you can have. So shift the parent function down 3. Okay. So what we just did is examples of vertical shifts. Okay. Notice the operation you did and where you did it. You did adding and subtracting, and you did it on the end of the function. Okay. That's what causes a vertical shift. Okay. So as I said before, these are rigid motion transformations. Okay. Rigid motion means you don't distort anything. You just move something. Okay. And the idea here is that if you have y equals x squared plus k, if k is greater than 0, it'll shift up. If k is less than 0, it will shift down. Now, I wrote shift down absolute value of k units because you don't want to say something like shift down -2 units. That's confusing. You shift up 2 units or you shift down 2 units. You don't ever shift a negative amount of units. Down takes care of the negative. Same thing with left and right when we do that. Okay, you can shift right 5 units, you can shift left 5 units. But don't shift left -5 units. It's kind of confusing. Okay, so any questions on when a graph would shift up or down? Okay, so let's take a look at this. I'm doing adding and subtracting again. What's the difference between what I'm going to do here and what I did here? That's x squared plus 2, x squared minus 3. Well, I've got a plus 2 and a minus 3 here as well. But what's the difference? Chris?
Yeah, parentheses.
Okay. And what else? Focus on the operation you're doing and where you're doing it. Where are you doing it this time? Oh, Brandon? Well, where did we do it last time? So look back at this one. I said that you added or subtracted something onto the end of the function. And then we went through all that stuff. Right. So now, where are you adding or subtracting this time?
You would
put it after the x squared.
It's inside the parentheses, right? So you're adding or you're subtracting, but now it's in the parentheses. So, did anyone have a guess what the minus 3 or the plus 2 is going to do this time? It is not going to shift up and down. Yep.
The minus 3 will move it to the right 3 units, and the plus 2 will move it to the left 2 units.
Okay, let's try it. So you said the plus 2 would move it to the left,
Yes.
right? Let's just do that one and see what happens. So let's do x squared, I'm sorry, x, just do it like that, plus 2, close parenthesis, square it. Now why do you think left? Because usually when I think plus, like plus goes to the right.
There's no from last year.
You just know, okay. So he is right. There's your original, and plus 2 is going to move it 2 units to the left. So minus 3 is going to move it to the right, which is kind of the opposite of what you would think. When I think of plus, I usually think it goes to the right, but it's not the way it works. So, for this one, to get y equals x minus 3 squared, shift y equals x squared, let's see, minus 3, shifted it right 3 units. All right, and now to get the other one, let's see, that's going to be left 2. So to get y equals x plus 2 squared, shift y equals x squared, left 2. So these, again, are more rigid motion transformations. Okay? Meaning we're not stretching, we're not distorting anything. We're just taking what we have and we're sliding it somewhere else. So there's a couple ways you can try to think about which way is left and which way is right. This one that we did right here, y equals x plus 2 squared. You could think of it as x minus 1 if you didn't want to write it as a plus 2. How else could you write what's inside there? With subtraction. So if you didn't want to write plus 2, that's the same as minus, yeah?
Minus 2.
Minus 2, all right? So some people, when they do this, they think of it always as x minus, right? And then what they do is just look at the number that's after the minus sign. In the top case, it's a 3. In this case, it's a negative 2. This only works if you always write it with a minus. If you always write it with a minus, block the minus, and then look at what's left, 3. Tells you it's going to go 3 units right. If you block everything here, block the x and the minus, you're left with a negative 2. Negative tells you 2 units to the left. Okay, so that's one way you can think about it. So if you always write it as x minus, then look at just the number that I'm circling. If that number is greater than 0, it will shift right. If that number is less than 0, it will shift left. Or, and I would just remember it one way or the other, because if you try to think of both ways I'm telling you right now, it's going to confuse. Or if you just write it with either a plus or minus, remember it's the opposite. Okay? So like if you see a plus 2, think in your head, okay, plus is really going to go left 2. If you see a minus 3, right 3. Okay, you just have to come up with a way of thinking about it that works for you. Okay. Any questions on that? Yeah.
When you're talking like the full quadratic that you plug into the calculator, what number are you actually changing within that, like x squared, x, or the
So when you're talking about like this ax squared plus bx plus c thing?
yeah, which number are you actually changing to move it horizontally?
Well, you're not really changing any of those numbers.
Okay.
Because, I don't know if we're going to, yes, I'm going to talk about that. I'm going to mention that.
Okay.
Because if you had a problem like this, 3x squared plus 12x minus 18, this one is very clear. A, B, C. You can tell which one is which. Because that equation is not written like one of these. And I'm going to talk more about that.
All right.
So, it's a good question. All right. So, there's our horizontal shifts. Now, this is an example of basically everything we've done so far. A is your vertical stretch. H is your shift left and right. And I used K for the shift up and down. Out of these three letters, A, H, and K, only two of them actually affect where your vertex is going to go. Does anybody think they know which two letters there affect the movement of the vertex? Yep.
Were you saying apart from H and K? Because
Yeah, just 2 out of 3 of these letters that I just circled.
H and K.
Only H and K, correct. A has no effect in this format on where the vertex is going to go. You can make A 10, you can make A 50. It won't make a difference where the vertex is. What does make a difference is H and K. Now, when I say H comma K, I'm going to circle exactly what I mean. This is H. Okay. This is K. So H is the number after the minus sign. K is just whatever the number is at the end, the whole thing. Now, yesterday we talked about horizontal and vertical lines. Does anyone remember the equation of a vertical line started out as this letter equals? Yep.
X equals.
X equals. So when I ask you to find the line of symmetry for a parabola, normally it's x equals 0. That's when the parabola is right at the origin like this. X equals 0 is just the y-axis. But if you shift the parabola, the line of symmetry could change. Now, let's go like this. If I shift the parabola up, did that change my line of symmetry? No. So shifting up and down has nothing to do with the line of symmetry. So K doesn't matter. The only thing that affects the line of symmetry is if you move it left and right. H. That's why the line of symmetry is x equals h. Okay, so let's try a problem where we write down the vertex and line of symmetry. Okay, so let's start with the vertex. So remember, vertex is h comma k. But we got to be careful. What is h in that case? Yeah? It's -2. Because the vertex is always the number after the minus sign. Well, I don't even see a minus sign there. Okay? So write it like this. And now, block everything that's x minus and look at the number you have left. So you've shifted left 2 units. And what about k? What's my k going to be?
-3.
-3. Yep. So there's your vertex. Number after the minus sign, comma, number at the end. Now, line of symmetry, it's x equals, and it's one of the numbers from the vertex. In this case, Emily, it's going to be x equals, let's go back, so it's x equals h.
It's 2.
Nope, not quite.
Negative 2.
-2. But those probably all would have been choices on a test. Like if I gave you a multiple choice question here, for line of symmetry, I would give you a choice x equals 2, x equals -2, y equals 2, y equals -2. So you have to know it's x equals -2. All right, so now we're getting into transformations where order matters. So leave maybe 2 or 3 lines under example 6, and then below that you can put down the order. So the order that we always do transformations in, when you write them, is you start with the horizontal shift, then you do vertical stretch and shrink. The next thing you write down is a reflection. And I put if necessary. These are all if necessary. Maybe you don't have a horizontal shift in your problem. Okay, so do your reflection if you have one. And then lastly, do your vertical shift. Notice there is no reflection over the y-axis. We didn't do that one with parabolas because it kind of looks the same. That's why we didn't do it. And we didn't do a horizontal stretch. If you're wondering, well, where would horizontal stretch fit in? It would be right here. I'm not going to write it in today, but we'll look at it later. But that's where horizontal stretch would be. Okay, so let's write down our transformations in this problem. How can we turn x squared into 5x squared plus 4? Okay. First thing is, can anyone tell me how many transformations I'm doing? You don't have to tell me what they are yet.
2.
Yep, I'm going to do 2. Okay, and let's go through the order. Horizontal shift. Brandon, do I have a horizontal shift here? No, there's no horizontal shift because that would be adding or subtracting in parentheses, like up above here. Okay, so we don't have that. Do we have a vertical stretch or compression?
Yes.
Yes. Which one?
Vertical stretch.
By how much?
By 5.
Perfect. So vertical stretch by factor of 5. Okay, next thing, do I have a reflection? No, what would be there if I had a reflection?
Negative.
I'd have a negative in front of the 5. There's no negative. And lastly, do I have a vertical shift? Anything, Jared?
Yes.
Yes?
4.
4, which way?
Up.
Up. Shift, up, 4. Yep. And that's the answer to example 6. Okay, example 7, same kind of thing again. Let's describe the transformations, and then we'll do vertex and line of symmetry. And then I'm going to do the last thing, which is going to answer Eric's question about, well, which letter did we really just change? And that'll be the last thing. Okay, how many transformations am I doing here?
3.
No, not 3. Have another guess? Yeah.
Oh.
Just 2.
No, it's more than that.
4.
4. The 1, the 3, the negative, and the 4. Each one of those is going to do something separate. So you're going to have every single one of them. How about, Eric, what's going to be my first transformation?
+1 on the x.
So which way is it gonna move and how much?
Right on the x.
So it's gonna move to the right
By 1.
by 1. So shift right 1. Good. Second thing. Who can tell me the second thing that's gonna happen?
Vertical stretch by a factor of 3.
Yep, vertical stretch by factor of 3. Good. How about the third thing? Yeah.
It's gonna shift like 4.
That's going to be the last thing. So we are going to shift up 4. But that'll be the very last one we do. Yep.
Reflection?
How?
Because they're a negative.
How is it going to reflect?
Reflect from, I forgot what it is. I forgot what.
Elias?
Reflect over the x-axis.
Reflect over the x-axis. Reflect over x-axis. Okay, now the vertex. Well, the vertex would have been at the origin, but what is the coordinate if you start at the origin and go right 1 up 4? Where do you end up?
1, 4.
1, 4. Right 1 up 4. Now, your line of symmetry normally would have been x equals 0, but you shifted your line right 1 unit. Now your line of symmetry is x equals 1. Shifting up and down has no effect on your line of symmetry. All right, so if you look back at all the problems we've done, they've all had a set of parentheses and squared, okay? Let's look at either a set of parentheses squared, or they just had like a number squared and then +4. Let's say you took something like, let's go back and look at, let me find a good one. This one, y equals x plus 2 squared. Let me just copy that down to a blank area. Now, let's say somebody took that and FOILed it all out. Y equals x squared plus 4x plus 4. This is a pain to work with, right? That's not as easy. I can't tell that you've now shifted it 2 units, right? I can't tell that because you FOILed the whole thing out. So if you get a problem that's been FOILed out, it's no longer in standard form. What we want is standard form. Right? So standard form makes it very easy to see, okay, what did we change, right? Did we shift it up, down, left, or right? When you put it in this form, then you can see the A, the B, and the C. But FOILed out, it's like the B and the C just kind of disappear into standard form. There is no B and C. There's an A, an H, and a K. The B and C just kind of get absorbed into that. You can't tell which one is which. So, if you are given a problem where it's been all FOILed out, right, and it looks like, you know, something x squared plus something x plus a number, like example 8 we're going to do. This is no good. You can't tell your horizontal shift and your vertical shift. The only thing you can really tell by looking at that is vertical stretch by a factor of 3. That's all I can tell you. I don't know anything else just looking at it quickly. So, if it's been FOILed out, how do we fix it? How do we reverse FOILing it out? We have to complete the square. Okay, so I'll write down the steps as I do this. But I'm really just going to show you how to do it as an example. Now the important thing to remember is if you do something on the left, make sure you do it on the right. Keep the equation balanced. let's see what happens. So, this one says describe the transformations, shifting and stretching. Because it's in ax squared plus bx plus c, makes it very difficult. We have to complete the square. Alright, so first step to completing the square is, I like to just get it equal to 0, okay? Which it basically is right now. Everything is on one side, y is by itself on the other. So over here, get equation equal to 0. That's step 1. Step 2, if you're completing the square, is to put the constant on the other side. Okay? So put the constant on the other side. So how would you move negative 18 over to the left? Yeah. Add 18. So 18 equals 3x squared plus 12x. So put constant on other side. Okay. Now, this next step only happens some of the time, but it does happen in this one. That number can't be there. If you want to complete the square, that number has to be a 1. Has to be. Can't be a 3. Can't be a 2. It's got to be a 1. So the left is fine. But what we have to do on the right is factor out the number that's in front. So what number do I have in front of x squared?
3.
3. I'm going to factor it out. Now you might be saying, well, what if 3 doesn't factor nicely out of the next number right here? What if that number was a 13? Well, then you'd get some pretty messy fractions. Okay, I'm not going to give you one like that. So this number will factor out nicely from the number right there, the 12. And that's what we have now. Any question on that stuff? So what did I do there? I made the coefficient of x squared a 1. So make coefficient of x squared a 1. Now we're ready to complete the square. So this is where you're going to add a number to both sides. You don't just pick a random number. Okay? The way you figure out what number to add to both sides, and you'll see why we're going to add this number in the next step, is you look at this. You take half of that number and square it. That's the magic formula. So what is half of 4?
2.
2, and then square it. I added 4. So take half of, how can I say this? That's the coefficient of the linear term. That's the coefficient of the squared term. That's the constant. So take half of coefficient of linear term and square. And that's what you add to both sides. So we just added a plus 4. Now be careful. What's on the outside of the parentheses?
3.
A 3. So what did I really just add on the right-hand side? I didn't add plus 4. I added 12. And that's the part that will mess people up. You added 4 times 3. Okay, so you added 12 on the right, so you're going to add 12 on the left. And that keeps it balanced. So you really just added 12 on both sides. Now, watch what happens on the right-hand side, and all of a sudden it's going to start to look like the kind of equations we've been using all class. On the right-hand side, x squared plus 4x plus 4. This is going to factor nicely. It's going to factor into two things that are the same, like x minus 8, or x plus 12, x plus 12. Does anybody see how this factors on the right-hand side? Emily?
X plus 2.
Times. Like if you were factoring it, it would be like x plus 2 times x plus 2. It's the same thing twice. That's always going to happen if you complete the square correctly. So the way we just write it is like this. X plus 2 squared. Now you can see a horizontal shift of 2 units. Couldn't tell that before. Now we can. And what's it equal to on the left-hand side? 30. That's basically my vertical shift. Okay? Just put it back on the other side. So 3x plus 2 squared. Now minus the 30 back to the other side. And there is your equation in a form that now we can figure out stretching and shifting and all that stuff. Right? So that's how you complete the square. All right. So real quick, someone just tell me what's my first transformation here. Yep.
Oh, horizontal
So yeah, shift.
shift, right, left 30. Oh no,
That 30 is going to be the last
left 2.
left 2. Yep, always start in the parentheses. Shift left 2. Who can tell me my second thing? Chris?
Something to do with vertical stretch.
Yeah.
I forgot how to say it.
Yeah.
By a factor of 3.
So vertical stretch by factor of 3. And what's my last transformation? How about Caleb? Can you tell me my last one?
That'd be shift right 30.
So we already did the left and the right.
So that'd be up.
No, not up 30. Yep,
Shift down 30.
down 30. So shift down 30. Now, that 30, you couldn't, if you look at the original problem, that 30 isn't in there anywhere. So you can't tell when it's written like this what you've actually done to it. So you have to complete the square. Any questions on that? Alright, so that's the homework on page 56. And there is a question in there about something we didn't talk a lot about today. So if you get stuck on one of them, don't worry too much. There's one thing I'll mention to you tomorrow when we go over them.